Today, we will be joined by 4 panelists. Our host, Tom Chmielenski, one of our speakers, Giacomelli, another speaker, Hala, and Marty, Matlock. And our first speaker up this afternoon, is Tom. And Tom is a software advisory engineer with Bentley Systems, and he is our host and master of ceremony for today. He received his master's degree in computer-aided engineering and management, as well as his bachelor's of science in civil engineering from Carnegie Mellon University. He is a registered professional engineer in the Commonwealth of Pennsylvania, and in his current role at Bentley Systems, Tom is researching new ways to use mobile and wearable technologies in the architecture and engineering design process. And he has been involved with the Future City competition as a mentor for 5 years now. Tom, welcome to our webinar.
Thanks, Thea. I would like to welcome you all to this Future Cities webinar. I will be your host and hope you look forward to hearing from our exciting 3 speakers that we have lined up for you today. Next slide. That's just me. Next slide. A little background about myself. Years ago, I was in middle school myself. We didn't have the Future City competition, but we did have a similar competition called Olympics of the Mind. We made it to the final competition, but we did not win. I loved the teamwork and the competitions, but more importantly, I made friendships that I still have today. Next slide. So when I was younger, I had 5 mentors. The first 2 were my mom and dad. They challenged me to work hard and follow my dreams. And it wasn't until I graduated that I realized they were my 2 greatest mentors. The second was my high school guidance counselor. When I told her I wanted to go to Carnegie Mellon for college, she said, "Wow, we never had anybody go to Carnegie Mellon before." She challenged me to be the first to attend and graduate from Carnegie Mellon, so I did. Next slide. When I started Carnegie Mellon, I wanted to be an architect. I studied architecture for a couple years and then switched my major to civil engineering. I enjoyed problem solving much more than I enjoyed freehand drawing. I found 2 really great mentors in college, Professor Dan Rehak and Professor Jim Garrett. Besides challenging me, they encouraged me to apply for a job at IBM, where I fell in love with computers. If it wasn't for them, I probably would be leveraging computers today to solve engineering problems. I guess the lesson here is pay attention to your teachers now and your professors in college, as they can point out opportunities that you might miss yourself. Next slide. As Thea mentioned, I've been a mentor with Future Cities competition for the last 5 years. I really enjoy working with the students and love hearing how the students iterate over their designs leading up to the competition. I encourage you to leverage your mentor's time and ask questions. Mentors love to problem solve and share their world experiences with you, and their knowledge will help your team build a better future city. That's me way in the back there. Next slide. Let's talk a little bit about the engineering process. This process is the general process that engineers use to solve problems. First, we need to identify the problem. What problem are we going to solve, and what are the constraints? This is the easy part for us. The Future Cities organizers have already outlined the problem on the website. They've also described the constraints in the rubrics on the website. I encourage all the teams to review the rubrics to ensure your team understands all the constraints. Research others' work. Start researching the web. Start searching the web. Read up on the latest research. Find out what others are doing in this area. Start talking to your teachers, your mentors, and your peers. Take some field trips to relevant areas. Has anyone tried to solve a problem like this before? Next, generate ideas. Be creative and brainstorm for ideas. Maybe someone has solved a slightly different problem. Go back. Maybe others have solved slightly different problems that could be applicable to ours. Maybe we could leverage a technology that was originally invented for something else. Could we improve a previous solution by creating it faster or cheaper or even more advanced using today's technologies? Then we try to create a solution. We decide on the best ideas and put them together in a solution. Always keep referring back to your original problem statement and ask, does this idea solve the problem? Some ideas sound really cool at first, but it may not help to solve the problem. Once you've created a solution, you need to test and verify your solution. Does it actually solve the problem? Does it stay within all the constraints? Present your solution to others and ask them for feedback. Then try to make it better. Most engineering projects are not solved on the first try. How can the team create a better solution to this problem? Incorporate everyone's feedback and generate new ideas and restart. What's important here in the engineering design process is this is an iterative process. The best solution will not happen on the first try. This is the same process engineers go through every day. So keep this process in mind when you are working on your future city. I encourage each team to keep iterating on their solution all the way up until the competition. Next slide. So I will leave you with some advice. First, ask your mentors lots of questions. They take the time out of their busy schedules to make themselves available to you. It's free expertise, so make the most of it. Work as a team. This is the one of your first of many opportunities to work as a team. You will get to see how your peers can come up with different ideas to the same problem. Remember to respect each other and value their opinions. But most of all, work hard and have fun. Good luck to all the Future City teams, and I hope to see you at Nationals in February. Now I'm pleased to introduce our first featured speaker for today's webinar, Dr. Giacomelli. He is the director of the CEAC, or Interdisciplinary Education, Research, and Outreach Program for Greenhouse and Other Advanced Technology Systems. He received a PhD in Horticulture Agricultural Engineering from Rutgers University in 1983. Dr. Giacomelli has designed, constructed, instrumented, and operated various types of economically controlled greenhouses utilizing hydroponic-based crop production, including NFT, EBB, and flood, and aeroponic systems for greenhouse lettuce, tomato, strawberry, and other numerous crops. His professional activities have focused on controlled environment, plant production systems research, design, development, and applications, with emphasis on crop production systems, nutrient delivery systems, environmental control, and labor productivity. He has designed and provide operational support with Sadler Machine Company in Tempe, Arizona for the first automated food growth chamber at the NSF South Pole Station in Antarctica between 2004 and 2013. Gene?
Yes, I'm here. Thank you, Tom, for that introduction, and Thea as well. Next slide, please. Hello, there we go. I'm excited about being here. I appreciate the opportunity. I want to speak about controlled environments, and I have a passion for them, but main reason is that ultimately they will produce food, and we all need to eat, at least several times a day. I do it more than most, it seems. Next. I come from the Controlled Environment Agriculture Center here in Tucson, Arizona. You see some of our students and faculty in this picture, so we are real people working on real problems with the goal of effectively using resources, limited resources. And you see them listed here on the right: energy, water, plant nutrients, labor, capital, that means dollars, money to be invested to build things. These are valuable and limited resources. All the slides will have this format, and at the bottom you'll see live links to specific locations on the internet that I would encourage you to go back and look when you have the opportunity. Next. The Controlled Environment Ag Center is for educating young people, doing research, that is getting more information, doing demonstrations to verify that what we have designed, what we have envisioned, actually works. And then developing applications. For example, you see a photograph here of Village Farms, a very large greenhouse located in Texas, growing tomatoes. Something on the order of 600,000 pounds of tomatoes every day in their 100-acre facility. That's a lot of tomatoes. There's a link at the bottom so you can go and find more information on your own. Next. The focus remains on the plant. If we want to produce food for people, we need to understand biology and we need to apply that to the plant. So a lot of my next series of slides will give you concepts along that line. Why are we doing this in controlled environments such as this head of lettuce grown hydroponically in a greenhouse? For high quality, guaranteed safety and secure food that is available. We also get very high yields, maybe a factor of 10 times more than you do in the open field. Plus, pesticide free. We don't have to spray pesticides and chemicals to control insects. Along that line, we use land, water, and nutrients more efficiently in this types of systems, and we can have a predictable harvest. And really, how much harvest we will have, we know in advance. Next. Why urban agriculture? Well, urban agriculture is a new direction in agriculture, and the logical response is, well, that's where the people are. Let's grow the food closer to the population and therefore reduce transportation costs, improve quality, have harvest the same day as sitting down at the table eating the product, eating the food. This, however, will be a complement to the traditional soil-based agriculture that we have spread throughout our country and throughout the world. It's not a replacement, it's a complement. You see an example of a greenhouse in the yellow rectangle on top of a roof in New York City overlooking the Manhattan skyline. We'll talk more about this later. Next. Fundamentals of plant growth. The seed has the genetic potential to grow, thankfully. All we do is provide the environment, sit back to some extent, and watch what happens. There's two environments you have to be careful of, the aerial environment and the root environment. The aerial environment, the parameters such as air temperature and humidity may be obvious that we want to control. CO2, carbon dioxide in the air, and the light available for plant growth may be a little less obvious. Air movement to exchange the CO2 and oxygen from the plant is also important, and something to support the plant so that we can move it around and harvest. Plus, we need access for labor. On the right-hand side, we see sand culture. We're growing lettuce directly in pure, very similar to beach sand, and use drip irrigation to provide nutrients and water. Next. The root environment is a second and similar. Water has to be there, nutrients dissolved in the water, plus oxygen dissolved in the water. The temperature of the root zone, water has to flow in some way, be brought to the roots and brought back. We want to keep the roots in the dark and have some physical support. We see deep water culture and Justin holding up an entire tray of plants with the roots hanging underneath. Next. All of these factors are important for you to design a good growing system. For example, here in hydroponics, you need to be able to pump water around, distribute that water throughout the system to all the plants, directly to the root environment. Plus, in hydroponics, we can collect the water and recycle it, bringing it back to a nutrient storage tank. Next. Different types of hydroponic systems are named here, and I ask you to go and look each one of these up. They have their benefits, and they can be utilized in a special way depending on your needs. All of them are soilless culture, that is without earth or soil. You see an example of aquaponics where Jason is holding the tilapia fish as well as a very large head of romaine lettuce, which was grown by the waste from the fish in the aquaponics system. On the right-hand side, you see the lettuces that are floating on those tanks of water. Next. The controlled environment is the aerial environment, and you see this picture here where the shell and the cover is shown. The light has to come through the transparent glazing to get to the plants. I can see the heater and the cooler. You'll learn what they are in this picture down the road, I believe. Humidity control, transport procedure is also, you see some overhead gantries in here. Harvest procedures are also indicated. Cleanliness and safety are all a part of growing in controlled environments. We know exactly what goes in, we know exactly what comes out, and we can predict that. Next. 3 types of controlled environments that are generalized. A greenhouse. You see a high-tech greenhouse on the left and a low-cost, high-tunnel greenhouse technology on the right that's actually growing in the earth of someone's farm, where the high-technology greenhouse is growing in hydroponics. But essentially the greenhouse is using solar energy to provide light for the plants. It is commercially viable and used today very much around the world. Next. A growth room or a plant factory is indoor, using no solar energy to grow the plants, but growing with artificial lighting and hydroponics. You see some of the benefits with the plus signs here, particularly minimal land usage. Water use efficiency is very high, pesticide-free produce, year-round production anywhere, even in the Antarctic. But some detractors: cost, high installation and energy costs. So these need to be further developed. We also need more experts, you, to learn how to operate these systems and to design them. Next. Finally, the vertical farm, and I put this in, it's very similar to the previous slide, but the word is being used, growing indoors with artificial lighting, in particular the LED lighting that you see, the pinkish color at this example of Green Sense Farms. And I'm particularly proud of this because one of our students, Lane Patterson, is now working there as the grower manager. The business viability of these systems, particularly vertical farms, is yet to be verified. We're looking forward to that in the near future. Next. Examples of real working systems. This is the Gotham Greens greenhouse that I showed you in New York City. This is Jen Nelkin, another one of our graduates. Brooklyn, New York, growing leafy greens, primarily lettuces and basil. Example here, 40 to 45 lettuce heads per square foot per year. That would be about 4 plants per square foot every month, every 30 days. You would do it 12 times. 4 times 12 is about 48 heads of lettuce per year. Very high yield. Again, about 10 times in the open field. Next. Loofah Farms. I think you'll hear more of that from the next speaker, but an example in Quebec, Montreal, Quebec, Canada. I put some numbers here. I'd like you to go back and look at their design, their size, their number of plants, 40 different types of vegetables, and the weight of harvestable crop that they do every day, and they do it all with only 6 workers. Important. Labor is key as well as light in these growing systems. Next. The food chamber at the South Pole we built and put it together in 2004. It's been growing hydroponic vegetables since that time, and I put some numbers here. 48 pounds harvested per week, and that's edible harvest. We're not counting the roots here. In 240 square feet. The idea is that we have fresh veggies where you could never have that before. It is also a bright and humid place to grow the crops, fresh fragrances. They're allowed to be gardeners. In fact, they clamor to be able to work on the plants because the psychological benefits of working in an extremely stressful area where there's no sunlight at all throughout the winter. It's great to see this warmth, the bright lights, and the green growing plants. Next. Example of the lunar greenhouse. We're not on the moon yet, but we are in our laboratory across the street. Again, production here is shown using artificial lighting, and this is designed for NASA, so it is collapsible. It is about 18 feet long. It collapses to about 6 foot wide. You can see me standing on the left side of the picture to get some scale, but the idea is to grow the vegetables to provide food, but also fresh water that comes from the plants, and oxygen to replace the carbon dioxide that the astronauts breathe out. Next. And my last slide is about Earth's sustainability from all these projects, and particularly the lunar greenhouse. This documentary was made, and you see a number of our students and staff and faculty that were a part of that. If you go to this Earthlight website, you can see this 23-minute documentary that links controlled environments to the sustainability of growing food on Earth, and the fact that if we can learn to do it on the moon and Mars, where resources are even much more limited than they are here on Earth, then we're going to be better off sooner, and that's what we need to do. Next two slides are all references to all the web links that I provided throughout the presentation. And I'll say thank you very much for this opportunity. I enjoyed it very much, and I wish you best of success in all of your work. Thank you.
Thanks, Dr. Giacomelli. That was a very informative presentation. Our next presenter will be Dr. Hala. After obtaining a PhD in agriculture engineering, Hala worked as an academic researcher at the Ontario Ministry of Agriculture. She published her research on using earthworms and electricity to turn waste into fertilizer in peer-reviewed journals. She has been cited over 230 times. She also authorized government fact sheets on processing of organic waste. More recently, she developed products for urban farming, including a suspended urban garden. The goal behind the products she developed is to turn kitchens into micro-farms where waste is processed and used to fertilize indoor vertical gardens. Hala?
Hala, if you've muted yourself, you need to unmute yourself because we cannot hear you. Hala, are you trying to speak? All right, so it seems like we're having some technical difficulties with Hala and her microphone. I'm just going to double check that she hasn't sent us an email, and if not, we might skip ahead to Marty Matlock's presentation and then come back if Hala is able to get her audio to work. Oh, we're hearing one moment from Hala. I just got an email from her. I apologize, everyone, about this delay. So, you know what? I'm going to use this time to ask Jean a question that we got. We got a couple of questions, Jean, so let's just use this time wisely.
Certainly.
We had a question here that said, where is it? What is the difference between hydroponics and aquaponics? Alec asked that.
Oh, Alec, good question. Hydroponics is growing plants in water without soil. Aquaponics is growing both plants in water without soil, plus connected to fish that are obviously growing in water without soil, no pun there. And the fish provide the nutrients from their waste in the water, and that water from the fish is cleaned, purified, by bringing it to the plants, who then use the nutrients, and you return the water back to the fish, so in a more clean condition. So aquaponics, you get a crop of fish and plants. In hydroponics, you're only growing plants.
Right.
Hi, sorry to interrupt. Can you hear me?
Oh, we can. Excellent. Welcome, Hala.
Okay, perfect. I have no idea what just happened. I redialed. Sorry about that.
Okay, so Jean, thank you for that fabulous answer. And Hala, we're going to turn it over to you.
Okay, so thanks for summarizing my background. Just a clarification, I was mostly a researcher at the University of Illinois and Penn State University, and I worked for a short while at OMAFRA, the Ministry of Agriculture in Ontario. I've also done some research and tried to develop products for urban agriculture, and I'm going to briefly go over how it's defined, where is urban agriculture done, what are its special requirements, and then I'm going to give you an example of a simple technology, a type of technology that can be developed to make urban agriculture accessible to everyone. And next, please. So urban agriculture is typically done within or near the city, in land near buildings, on rooftops, on walls, inside indoor floors of buildings, and in vertical spaces, typically indoors. And out of all of these options, as Jean mentioned, the most economically feasible is the type that happens indoor because it's the most controlled and the most productive. And what you see here is a picture of the Edit Tower. This is a project in progress in Singapore, and it combines elevated gardens, farms, and apartments. Next, please. So one particular thing about urban agriculture is that it happens close to people, so there are restrictions. For example, pesticides cannot be used in such an environment. They have side effects on human health, and they need to be avoided. Of course, in most indoor controlled environments, plants are naturally safe from weeds and pathogens, so pesticides and herbicides are not as necessary. Also, labor is costly in cities, so mechanization is necessary. Another aspect is that urban consumers want sustainable produce, typically food that was produced without harming the environment. And another aspect is that there's no need to transport the food over long distance, so it can be harvested ripe, which allows it to be tastier, and that lowers the cost of transportation. Next, please. Oh, sorry, and this is a picture of a design by Bright Farm System, and this is something planned for a location in Masdar city in Abu Dhabi. Next, please. So the next question is, how is urban agriculture achieved? And there's emphasis on the equipment use. The equipment needs to utilize vertical space because footprint is expensive in cities. One way to do this is green walls, suspended gardens, or shelves. And here you see an example by Verticrop. These are rotating shelves that bring the plants to a wiring station. Another aspect is the equipment needed to fertilize. This can be done through fertigation, where the liquid fertilizer is mixed with water. And in another type of farms, fertilizer can be recycled organic waste. So urban farms would then be a sink to food waste that is turned to fertilizer and then added to the plants. And it's a way to close the nutrient loops, to help close the nutrient loop in cities. Another important thing about equipment is its cost. So equipment doesn't necessarily have to be costly or very high tech to be effective. Something could be low tech and creative and reduce labor. Another important thing is that if the equipment is modular, there's no need for expensive infrastructure to set up an urban farm. And such farms can expand gradually as the budget permits. So a module is an element that you can use one of or 100 units of, and you can just expand that farm according to how much money is available. Next, please. So another relevant thing about urban agriculture is the structures used to use vertical space or to bring light to the plants. The structures need to be lightweight. They must weigh less than the maximum loads that roofs or building floors can carry. The setup could be soil-based or hydroponic. Soil-based might weigh a little less, but it has the advantage of being a sink for organic waste. The plants could grow on walls to use that space, so the structure can be a living wall, a green wall, and typically these are equipped with recirculating pumps to water the plants and recycle the water. And plants need light if they're indoor, and this can be brought to them through sun pipes. These are kind of grotesque fiber optics that bring sunlight from the windows to indoor space. And also LED lights can be used. I think a slide shown previously by Jean showed the purple light, and this is an example of LED lights used to grow plants. Next, please. So another important aspect is reducing labor because it is expensive in cities. This can be achieved by automating watering, by reducing weeding costs. So in a controlled environment, there would be less weed seeds, and also if plants are grown from seedlings, then they have a better chance of outcompeting weeds, and there will be less work to do for to remove the weeds. Another important time for labor is harvest, and mechanized system can bring the plants to the operator. So what you see here is an example by Urban Barns. It's called cubic farming. And this is a mechanized system that rotates the plants and bring them to the person harvesting them at one side of the cube. This is an example of a Canadian technology, and the other is Lufa Farm, also mentioned by our previous presenter. Also, there might be a need for equipment that handles organic waste in a hygienic, socially acceptable way, to compost without causing too much side effect in an urban location. So in the future, new technology is expected to simplify urban farming, and it will be people like you who develop such technology. Right now, it's still in the making, it's still emerging. Next, please. So new technology can be simple. As you noticed in many pictures we've seen before, that only one layer of the space was used to grow plants. That's because going vertically is expensive if complicated shelves are used. But one could go vertically using something simple like chains and cups, as you can see in this picture. This is an example of a design using cups, chains, and felt. It reduces labor for watering because it stores water inside cups and uses sub-irrigation to water the plants. It can be made using do-it-yourself instructions that are available online. In your assignments, you need to grow an animal protein, as I understand, and a vegetable, and these could grow in such a structure. And in an alternative design, watering can be automated in such a structure by using float valves and water lines, and without electricity. So sometimes automation is possible using mechanical system and not electrical ones, which makes such a design possible in places that don't have access to electricity. Next, please. Potentially, urban agriculture could be organic, and the FAO and previous researchers have found that organic farming, which essentially uses recycled waste in the form of organic fertilizer and has other features as well, that kind of farming produces more plants, more yield per input, and it maintains a healthy soil. And for later purposes, you can go back to the slides for specific references. Next, please. So, and I want to mention one more thing about organic fertilizer is that, again, it allows to recycle waste. So urban gardens not only would produce food in cities, but they would also reduce the environmental load of cities. The main idea is that anyone, anywhere in the world could use simple, accessible technology to grow a vertical, year-round edible garden. If that was possible, cities would look greener, would feel and be healthier, and would produce more of their own food. So in your assignments, I think you can imagine your own technology for all that can make urban agriculture more accessible. Next, please. So as a last picture, I wanted to show design planned for the year 2035 for Boston, which would green the city and take transportation underground, so it's mostly pedestrian friendly and green. I hope this image inspires you, and I hope you enjoy imagining a city lush with urban farms. Thank you.
Thanks, Dr. Chaoui, for taking the time to present to us today. Our final presenter for today's webinar will be Dr. Matlock. Dr. Matlock is Executive Director of the Office for Sustainability and Professor in the Biological and Agricultural Engineering Department at the University of Arkansas. He received his PhD in Biosystems Engineering from Oklahoma State University in 1996. He is a registered professional engineer, a board-certified environmental engineer, and a certified ecosystem designer. The focus of Dr. Matlock's research is to develop technologies and processes to increase the resilience and effectiveness of human-dominated ecosystems. His work encompasses urban agriculture and rural systems and has been recognized by the leading organizations in architectural, landscape architecture, and sustainable design with over 25 national and international awards. He coordinates academic research, outreach, and facilities efforts in sustainable systems across the UA campus and has led numerous sustainability initiatives from local to international in scope. Marty?
Thank you very much. I appreciate the opportunity to speak to you folks this afternoon. What a wonderful set of presentations you've heard. I hope that this will sort of bring it on home for you. I'm going to take Hala's presentation forward from the city level. But I do want to point out the role of engineers and architects in design are absolutely key to our future. My message fundamentally to you is the future is ours to design. Next slide, please. I'm going to talk to you about a project we did in our hometown, Fayetteville, Arkansas, where we tried to envision our future, because the future we'll have is the one we design. And if we don't envision our future, we'll get whatever happens. So we have to plan our future. That process of planning is an absolutely distinct activity. It's not an accident. It comes from lots of effort from lots of people. And this project you're engaged in is very appropriate for developing your skills in planning. We wanted to envision what our city in Fayetteville, Arkansas would look like if it provided most of its own food from urban agriculture. I worked with our Community Design Center, a group of planners and architects with my students who are engineers to develop this work. My students were not that much older than you. They were sophomores in high school. This project has been awarded 3 national awards from architectural organizations so far. Next slide, please. And these were from students not much older than you, to remind you. So that we have to think of the city as a growing organism. City has it has to have food brought in, it has processes internally, and it generates waste. And the city has a history like all organisms. So we first look at our city's history. So what you're seeing now are topographic maps, that's maps of terrain, with the red lines representing the growth of our city from the 1930s in the upper left to 2013 now in the bottom right, and you can see how much our city has grown, like all of your cities have grown in the last 100 years. That growth of our city in the past tells us about the challenges we'll have in the future. Next slide, please. If we continue to grow at our current rate, we will have a process called, or a phenomena called, sprawl. Sprawl is where the urban borders and boundaries grow out into the countryside, expanding in a radius like a circle, expanding dramatically the area that's contained, and the cost and the problems associated with delivering services, and for that organism, the town organism, to function. So rather than looking at sprawl as our future, which you would see from all the red lines out scribbled all out the streets that would have to expand, and the housing that would have to expand out in the outer areas into the fields, which are the green boxes, we envisioned a food city scenario where we had dense growth. If you can see that square that we had superimposed over the city with red and green, That's a food city design where we intensified housing integrated with urban agriculture. Next slide, please. Now, every city exists in a place. Place matters. Place matters because it determines climate, soil, and water. And as you heard from Jean and Hala, those are critical elements for determining what can grow where, because of the aero and soil environments for growing. These are critical to design. Place matters. You can see we mapped our soils. Topography are the black lines that show hills and valleys. Water is the blue, and we put our food city template on top of that to see where things could grow. Next slide, please. Streets matter too. Streets are the vascular system, the arteries and veins of the town organism. That's how we move people and things from one place to the other. So we must design our streets to serve our town to grow the way we want it to grow. Next slide, please. The town organism has to have food, energy, water, waste treatment, and people. And those have to be in a place, and they have to be connected by streets, and they have to be connected by other services. So we have to design those explicitly, or they will happen by accident, which is generally not good. So we envisioned our future city with discrete districts, those districts providing specific processes. Think of it like zoning, commercial zoning, agricultural zoning, residential zoning, so that we could have efficiency of scale for things we need, like aquaculture, composting, sprawl retrofits, which is where our most dense people housing is going to be, and then waste to energy. Next slide, please. The other thing we have to do is we have to move ag to the front yard. Urban agriculture can't be something we do in the backyard or in the factory. It has to be part of our culture, part of the things we celebrate in our public spaces, like in our front yard, our street easements. Next slide, please. And in our parks, because parks should be orchards. They should be places people go to celebrate the bounty of the earth, the things that we get from the earth that derive our subsistence and existence. They provide us with sustenance, and they provide us with a sense of connectivity of place. So we should design our public spaces and in such a way that they enhance that cultural value. Next slide, please. And remember, there is no such thing as waste. Waste is just something you haven't found a purpose for yet. Virtually everything humans create has value because it has energy in it. And we have to find better ways to recapture that energy to use it, whether it's nutrients in the soil, whether it's water, whether it's plastic products, petrochemical products. We can no longer continue to think of things as waste. We have to think of them as products that have yet to be purposed. And finally, next slide, please. Urban food makes money, and we all know that money matters too. So urban systems, urban agricultural systems, as we've already seen, are very productive, they're very efficient, they're very sustainable, they're also very profitable. And profit is a no-brainer in this country. If you can make money at it, we ought to be doing it. So my challenge to you is this fundamental question: why aren't we doing it? Last slide, please. I suggest to you that the future we experience in 20 years will be the future we design today. The design disciplines such as engineering, architecture, and urban planning are critical for developing our prosperous future. You are the designers of our future. Thank you.
Wow, this is Thea Saar from Future City, and I have to say that Jean and Marty and Tom and Hala, what a wonderful job you did presenting urban agriculture to our Future City students. So I'm going to be scrolling through these questions. So everybody, if you have a question for Jean or Marty or Tom or Hala, please enter it into the question box. And also, if you know who you would like to address, you could say, Marty, this question is for you, or Jean or Hala. and then I can make sure that I am getting it to the right person. So I am going to look for some questions. Here's a question. I don't know who it's for. I'm going to unmute all of the speakers right now. So Jean and Marty and Hala, you're all unmuted. What architectural designs are best for underwater farming and buildings? Or where is a place people can go to research that? Anyone want to take a stab at that?
This is Gene.
Sorry, go ahead.
Sorry. Yeah, this is
Go
Gene.
ahead.
NASA has a project off the coast, southern east coast of Florida, I believe, where they have an underwater facility where they're doing designs for habitation. And I don't know that they've moved any plant production into that yet. That's the only thing that came to my mind.
Okay.
This is Hala. The one thing that comes to mind is that algae is a very sustainable crop. It's a good source of protein, and I've read about it as an emerging crop when wheat will become more difficult to produce because we ran out of arable land. So this is a very good thought that someone had, growing food underwater. And one thing you could look up is algae production.
Oh, great. What are some factors to consider if they're attempting to farm underground? Going with the under theme.
Well, there's no sunlight underground. That's a challenge. So you either have to direct sunlight from above the ground to your crops below the ground in some way, or you have to have a source of power that can operate or power a lamp, like an LED light or other lamps, to provide the energy for the plant to grow. This is our example when we go to the moon. We will build an underground facility, and if you look to lunar greenhouse, if you Google that, you'll find our website about that.
And there's a follow-up question to that, Jean. Is artificial light better than natural light, or what are the pros and cons of each, I guess, would be a better way to put that.
Oh, how many hours do you have to discuss that? It's better and it's worse in many different ways. The positive side is that we will learn the exact colors of light, the wavelength of light that makes the plant grow best and most efficiently. And because, you know, white light is a combination of all the colors of the rainbow, but the plant primarily uses red light and green light. Blue light. And thus you'll see the LED systems, as you look them up, are either red or blue or somewhere in between with that purplish color. So we have the opportunity with those to make the plants grow more efficiently, but then you need a source of electric power. And electric power needs, at the moment, fossil fuels to generate the electricity. If you can go to photovoltaics to convert sunlight to electricity in an efficient way, then that would be ideal, and resolve the problem of the sun. The sun gives us too much energy and also heat that we don't need to grow the plant.
Nice. Hala, what are the pros and cons of vertical farming?
So I'm going to try to think of a con, but the pro is if it's happening close to people, besides producing food, it filters indoor air. It creates green space, which visually is relaxing and uplifting for people to see. I guess the cons right now is the expense, especially if a structure is dedicated to vertical farming, is designed and built just for that. But one way around this is to retrofit existing environments. So controlled environments allow for the most productive farms, but they are already semi-controlled environments, and these are our offices and apartments and houses. So if these are retrofitted to produce plants, to share them between people and plants, or in some cases just produce plants in them, then vertical farming is all pluses,
Great.
More than minuses.
Thank you. Marty, can you tell us more about the food distribution on the edible parks?
Certainly. The notion of a food distribution on edible parks is the food is a public resource, that you can harvest the food for your own purposes. Now, so you're in a park and the apples are ripe, you can pick an apple and eat it. Now that means that you can't really have people in a public system exploiting those commons for their own benefit. You can't have someone picking all the apples. So this becomes an exercise in sharing. Sharing is an important part of community ethics.
All right. We've got lots of questions on aquaponic facilities. And does anyone want to take up the question of energy intensive? You know, how intensive are aquaponic facilities?
I can do some of this as Gene. Yes. Well, any system you can design to have way too much power usage. That's why you need an understanding of the minimum amount you need, and to do it in a practical, low-key way. That's why I tried to express the important factors you need to control, at least at minimum, to grow the plant. And fish are actually more tolerant than plants in some ways, particularly the tilapia that they use. But you need electrical power for pumping water. You need power for bringing oxygen and air to dissolve into the water so that the fish have the oxygen they need to breathe. And the plant roots need that as well. If you're in a greenhouse, then in the wintertime you'll be heating that greenhouse in the nighttime when there's no sun to bring you the solar energy to warm the air. You'll also need some means to cool that in the summertime in the day when it's too hot. But you may not need electrical lighting, like with the vertical farms. You have to have electrical lighting. So these things are all have to be weighed and decided. What is your goal, and what is your productivity rate? The higher the rate, the more energy you're going to have to put in. So sometimes, many times, it makes sense to have a moderate production rate and then use less intensive amounts of energy.
Great. Thank you, Gene. Marty, look at this interesting question. What are some of the cons of urban farming versus traditional farming?
Well, traditional, what we call land-based farming, has all the benefits of an agroecosystem that has space. The cons of urban farming are largely associated with the cost of space. The fact that you have to do more on less space, that's also a benefit, but it's a challenge that you just heard Gene talking about, because growing things on less space often requires more energy input per area of space, because you can't wait for corn to grow in an urban system, for example. You can wait 180 days, half a year, for corn to grow in a farm on Iowa, but growing a crop where you only harvest it once a year and it takes 6 months for it to grow in an urban system is not going to be viable. So it requires more intensive activities, not absolute intensive activities, but more, and it's really because the space is more expensive.
Could I add to that?
Please.
I agree 100%. That's right on the mark. Our cereal crops, the grains, will still be grown in the open field. In the urban agriculture, you're going to grow crops that have a higher value, that turn over more quickly, that you get more production each day, and you harvest and you can replant and get something back. So the leafy green vegetables, the fruiting crops, tomato, pepper, that keep producing, but not the wheat, rice, corn, potatoes, that it's 180 days and you get one harvest and then you wait another 180 days. The space is too valuable. So you go for what they call the specialty, the high dollar value specialty vegetable crops. Makes a lot of sense.
Yeah. And I think this next question follows up. It's for you, Hala. What's the biggest benefit to vertical farming?
Well, it can create new types of jobs in cities, urban gardeners or urban farmers that sell their produce locally. There's the environmental benefit that I mentioned earlier. So the air is cleaner, the landscape is more pleasant to look at, less stressful for people, because looking at just cement and cars and pavement is actually stressful for human beings. It all depends on where the farms are located, of course. So there's the economical side, which is to create jobs. It allows a city to produce some of its own food, so it becomes more resilient in case there's fuel crisis or something that prevents food from being imported into cities. Another advantage is if those farms use recycled organic waste as fertilizer, then that would divert some of the waste stream, and it would reduce the ecological impact of cities, the environmental load of cities. Cities will become more environmentally friendly because they will export less waste.
Nice. Marty.
And
sorry,
could I add that the waste, a resource of the parts of the plants that we don't eat, like the roots and the stems and the leaves, if they're composted right on site, then eventually you can make more soil amendments. But you could also make compost tea, where you extract the nutrients that the plants need from that material, their previous generation of plants, and use those nutrients for the next generation of plants right on site. So you don't have to bring in more fertilizers. The same with water. You can recycle the water like we're going to do on the moon, because it's there. Use it once, reuse it again after the plant gives it back to you.
Right. Marty, what evidence do we have that urban agriculture is profitable?
It's very clear that in the United States, where we are seeing in cities like Portland, in cities like Boston, in cities like Montreal, we're seeing this emergence, a dramatic emergence of restaurant direct trade with urban agriculture. The demand for it is high enough that the products are being developed in urban systems. But I think the most dramatic example of this I have is yesterday I was in Denver with the National Institute of Animal Agriculture with aquaculture growers, and I met with a gentleman who's developing a hydroponics aquaponics system in Hawaii where land is $80,000 an acre. $80,000 an acre. That's 10 times the average cornfield cost of land, and he's still doing that profitably. He's making money. If he can make money there, and he makes it now, that demonstrates his profitability. His costs are exorbitant. Everything has to be flown in, and he's still making money.
Right. Is there a recommended amount of space you would say to set aside for an urban garden? Or another way to...
Small is beautiful, large. Yeah, I mean, I would say that they're fully scalable. They're fully scalable, and that's what's so cool. A small garden can be wonderful. It's not unusual to see a Thai restaurant that has a small spice garden out back that's no more than the size of a small bedroom, and that provides many of the spices they need year-round for them. Or to see something as large as some of the pictures that Jean and Hala showed you.
And is there like we've got a lot of questions about yield and how you calculate yield and what is a heavy yield. Is there an easy way to explain yield? We don't mandate in this year's essay that that any of the teams have to calculate out their yield, but rather that they've considered that the crop that they're selecting, or the crops they're selecting, will most likely produce a large yield. But how can students assess that and think about yield when they're looking at different crop options?
The only way is that without them actually growing it themselves and testing it, and that would take many years to get the experience to be able to get the high yields that are possible, is to look in the literature. I could, Thea, provide you with some common vegetables that I did a comparison between growing in a controlled environment greenhouse and compared to growing out in the open field, and I contrasted not only yields but actually water use. And the only way is to see what is commercially done at high levels, meaning not a small unit, but it usually would have to be something in the terms of acres of size or hectares of size, and see what numbers they get from their yearly production. That's the only thing I could say at this point.
Okay.
I'd like to add to that. Oh,
go ahead, Marty.
Just simply the metrics for yield, of course, are usually the mass produced in SI units or scientific units, kilograms per unit area, square meter. So that's the simplest way to measure it. But when you start talking about systems like Hala described, where you have vertical walls, vertical production, that gets a little more complicated. So you have to think about growing surface area. But the efficiency is another way to think about that, which is the amount of input it takes to produce mass. Efficiency is an incredibly important sustainability metric. So if you have to use a certain amount of water to produce a kilogram of crop, nitrogen to produce a kilogram of crop, or energy to produce a kilogram of crop, that efficiency metric is really your sustainability metric. Yield is your economic metric.
Very good point.
Right. I wanted to add to that as they pick their types of input, they should not necessarily try to be as low-tech as possible, but as low-cost as possible. So if they can bring sun from the window using a sun pipe, that's more economical than using electricity, even though there's a capital cost that's maybe high in the beginning, but then operational costs will be lower. And the other thing, another way to calculate yield is, depending on the technology they use, they could be growing several layers of plants. And they could use something creative like mirrors or something of that sort to bring light to all the layers of the plant. But they can, from the literature, find out how much can be grown on one horizontal plane, and from that, multiply by the number of planes they're using in a space. Number of levels, they're using in a space. Does that make sense? Like if they're growing on a floor, just one layer of spinach, there is data on different types of, a range of yields from low to high. And then they can take that average, and if they manage to grow 3 layers of spinach in a room, they multiply that by 3.
I'm going to take a few more questions, but here's one. In urban farming or rooftop greenhouses, how do we deal with soil pollution?
Grow hydroponically. You don't have any soil.
But I would suggest that the soil is, for organic pollutants, the soil will metabolize the bacteria. Soil is a living thing. It's composed of a whole bunch of different types of organisms, including bacteria, the zooplankton, and fungi and viruses, and they will consume amazing amounts of complex organic carbon. However, what really is the only soil contaminant I have concerns about really are associated with things that aren't consumed but can be concentrated, like heavy metals. Those are the ones that can be problematic in urban soil systems. If you accumulate heavy metals that can then be captured by the plant and then stored in the plant, that becomes a way for humans to be exposed to it. So except for heavy metals, I have no concerns about soil contamination. I think soil is a cleanser for ecosystems.
Right. This is a fun question. When plants are grown on rooftops, is there any way to protect them from birds or insects?
Bigger birds?
There's netting that you can put over to keep birds away, like they do in the tree fruit orchards. You could put them inside a greenhouse. There's no bird problem inside of any greenhouse.
I have major problems with deer on my surface orchards. Major problems with deer. I would love to have rooftop problems.
There's a sound mechanism to keep birds away in subway stations, and I think this applies in agricultural production too. The sound of a more scary bird is just played, and that keeps away the other birds.
But there's an ethical, sort of philosophical issue here too, which is an old agricultural concept: 2 for me, 1 for you, which is there's a sense that you don't that some predation or herbivory, some loss to these sorts of activities, as long as they're not catastrophic, as long as they don't introduce disease vectors like poo. Bird poo is a bad thing on crops. Then it's just part of your agro-ecosystem, and if we can't tolerate, we have to intervene. And I like mechanical protection, like Gene was talking about. but at a certain level, we're creating an ecosystem that other organisms need too. So there's a certain amount of sharing that is not a bad thing.
Marty, what are the pros and cons of cubic farming?
Oh, goodness, I think Hala showed the cubic farm, but I can tell you the pros are density. You get a whole bunch per volume. The cons are it's intensive and it's mechanized, and so you have to have it's a high tech technology-based process in order to manage it effectively. But I love it. I love the concept. So I think the pros of sustainability and yield efficiency far outweigh the cons. It just means you can't do it everywhere because you have to have a base level of technological capability. You got to have the tools, the equipment, and the smarts to do it.
Excellent. Well, thank you all very much. This was a very informative and entertaining hour. I learned a lot about urban farms, and I hope all of our student teams and educators and mentors that have shared this past hour are as equally appreciative of Jean and Marty and Tom and Hala and how much time you gave us all and your expertise that you shared with us today. I want to thank you, and I want to remind students and educators that today's presentation, a recording of this presentation has been made, and we will post this to the website by tomorrow morning. And we will also have the PowerPoint version of the slides up on the website. So all of the reference links that have been provided by our experts today will be available to you, and you can check that tomorrow. So thank you, everyone. Really appreciate your time and energy, and good luck, everyone, as you start to dive deeper into your urban farms and pick your 2 crops. Take care, everyone.
Thank you, Thea.
Best of success.
Everybody. Yes, it was very nice participating in this. Thanks.
Yes, it was fabulous. You all did a great job. All right, I'm going to stop the recording, and people are free to move about the country.